Hey, I'm Jeffrey Anthony. This is my Assignment 2 presentation. I am a solo group. Yeah, so let's get started. So overview, I chose two tasks that chain together. So task one is symbolic unconditioned generation, meaning that I'm generating a MIDI chord progression from scratch with no input. And I chose to do kind of jazzy inspired chords. But I want it to, at the end with task four, which I'll talk about, I want it to produce some kind of synth or pad using those chords. So the model just learns what like jazzy chord progressions are and what it sounds like from data, and it creates a new one. This output is a MIDI file. And then task four is continuous condition generation. So this takes MIDI pitches as inputs, and then synthesizes actual audio using a flow matching model. So it's just turning those symbolic chords into a synth that you can listen to. And then yeah, also what's pretty cool is that what comes out of task one is supposedly then being fed into task four. So task one is the MIDI, and then the MIDI is being used as an input for task four. So yeah, cool. So let's dive into task one. So for task one, for the training data, I pulled from three main sources. For some background, I've been producing music since 2020, and I already had a bunch of MIDI packs installed just based on my music production. And so, yeah, this Oshi MIDI pack I already had before. I've used it in the past in my own music, and I really like the sound of the chords that the producer Oshi used. And I kind of use that as like an inspiration. I found some more lo-fi jazz chord progressions that I had in my folders. And I also did find this huge GitHub repo of 7,000 plus chord progressions with a bunch of different, minor, major, and all the different kind of moods that it does. So 29 in the Oshi, 40 in the lo-fi packs, two of them, and then more than 7K in the open source repo. For pre-processing, I parse each MIDI file using the Mito library. I extract all the note on events at each beat position and group simultaneous notes into chords. Each chord gets represented as a pitch class set. So the notes are then named from 0 to 11, ignoring the octave. I filter out anything with fewer than two notes, since those aren't really chords. And then I transpose every sequence to all 12 keys, which multiplies the data set by 12, which gives us over 30,000 training sequences from the original files. And for the exploratory analysis, looking at the data, a few things stand out. So most of the sequences are 4 to 8 chords long, which makes sense. It's just typically like a 4x4 measure. And then it's usually 1 or 2 bars. And the chords themselves are typically, what it found was mostly 3 to 4 chords, 3 to 4 notes per chord. So we're seeing a lot of triads and seventh chords and ninth chords and whatever, which is exactly what we'd expect coming from like a jazzy kind of chord progression set. And then after the 12 key transposition, the pitch class usage is perfectly uniform across all 12 notes, which is good. Which means that the model won't have like a bias towards any particular key. And then we ended with 703 unique chord types in the vocabulary, which gives the model a lot to work with. And for the architecture itself, I'm using an LSTM, which is a long short-term memory network, as my chord generator. The architecture is pretty straightforward. First, each chord token gets mapped to a 64 dimension embedding. That feeds it into a two-layer LSTM with 256 hidden units. It learns the sequential patterns in how one chord leads to the next. And then there's a dropout layer at 0.3 to prevent overfitting, followed by a linear layer that outputs a probability distribution over the entire chord vocabulary. And the whole model is about 500,000 parameters. Okay, so let's take a look at our training and results. The model converged pretty smoothly. The loss started around 3.2, which is basically just randomly guessing across the vocabulary, and dropped down to 1.46 over 200 epochs. You can see the loss curve that most of the learning happened in between in the first 25. And then it gradually gets defined from there. And it also gave some example generated progressions. The first one, D, F, A sharp, which is a B flat major chord, I think. Moving into a bunch of other chords, and this is a very common like jazzy and like very common chord progression. Um, so yeah, that's pretty good. And then what's cool about the model is that it like clearly picked up common patterns that it found. And it's using sevenths, minor sevenths, major sevenths. It's using ninths even. But yeah, it was doing pretty good. And for the evaluation, looking at three main metrics here. First, it was 173 times better than random. That's just the improvement over baseline. So if you picked chords uniformly at random over our vocabulary of the 703 chords, you'd get a perplexity of 703. Our training model gets a perplexity of 4.05, which means that at any given moment, any given point in a progression, the model has effectively narrowed it down to four likely chords instead of 703 likely chords, which is obviously an improvement. Second, the 50 out of 50. I generated 50 chord progressions, and every single one of them was unique, using 47 distinct chords across all of them. This is important because it shows that the model isn't like memorizing the training sequences. And yeah, for the related work, okay, Music Transformer was one of the first to use self-attention for music generation. It handles long range dependencies really well. And I chose to use the LSTM over this because we are typically dealing with 4 to 8 chords. Um, if we were dealing with like full compositions of really long pieces, then the transformer would have done better. But yeah, that's why we used the LSTM. And then MuseNet from OpenAI showed that like neural networks can learn these like harmonic um, relationships at scale. They trained on a huge data set and could generate music in a bunch of different styles. Obviously, our approach is much smaller, but focused specifically on like the kind of feel that we wanted to do. So, which is like a jazzy chords. And then chord to MIDI is the tool that was used to create all of those like MIDI chords that I grabbed from the GitHub. Um, and Deep Bach was like a pioneer in using deep learning specifically for chord and harmony generation. They focused primarily on Bach, but the core idea of like learning the harmony patterns from the data is basically the same as what we did. Cool. So let's move on to task 4. The data from task 4 comes from NSynth, which is the natural synthesizer from Google. It's a huge collection of over 300,000 4-second audio samples covering 1,006 instruments over 11 families. And this includes like things like strings, brass, keyboards, synths, and everything. And every sample is labeled with its MIDI pitch, which is what we needed because our model is pitch conditioned. Also important to note, we will come back to this later, the sample rate is at 60 kilohertz mono. That leads into some limitations for us. And then we filter specifically for the keyboard samples because we want the synth pad sound for chord progressions, and the other ones wouldn't help with that. So for pre-processing the pipeline, we load each WAV file at 60 kilohertz. Then compute a short time Fourier transform or STFT to get a spectrogram that converts the raw audio waveform into a frequency over time representation. We split the spectrogram into its real and imaginary parts, giving us 2 channels. Then we normalize the unit variance so the model trains more stably. The final input to the model is a tensor of the shape 2 by 513 by 63, which just means 2 channels, 513 frequency bins, and then 63 time frames. Yeah. Okay, so for modeling, the model is based on flow matching, which is an ODE-based generative model. The core idea is that it learns a velocity field, so V of X and T, that defines how to transform just like pure noise into realistic audio along with like a straight interpolation path. That path is defined by this equation. And yeah, at inference, it starts from random noise at t equals 1, and then when t equals 0, it integrates the ODE backwards. So yeah, and then on the right, so the architecture is a unit with about 125,000 parameters, which is pretty small. The pitch conditioning works through film, which stands for feature-wise linear modulation. The MIDI pitch gets mapped to an embedding, and then that embedding is injected into each layer of the unit. So the model knows what pitch it should be generating at every level of the network. I also use classifier free guidance or CFG. During training, I randomly drop the pitch label 10% of the time, replacing it with a null token. Then at inference, we run the model twice per step, once with the pitch and then once without it, and then amplify the difference. That's this formula at the bottom. Yeah, and the scale factor S controls how strongly the model follows the pitch. So the higher value gives more accurate pitches, but it can also reduce the audio quality. And for our MIDI to audio pipeline, our first step was we take the chord pitches directly from task one's output. So if task one generates, for example, like an A sharp minor, we take those notes in that chord and then we get the individual MIDI pitch numbers for those notes in the chord. Step two, each pitch gets synthesized individually through the flow model. So for a 3-note chord, the model runs 3 times, once per note, and then it generates a half-second spectrogram for each pitch. And this is where the flow matching happens. And then step 3 is we layer the individual note waveforms together by summing them. So those 3 separate notes become one chord audio clip, and then we normalize that after summing, so that like nothing clips or nothing gets distorted or whatever. And then for step 4, we concatenate all the chord audio segments together in a sequence. Each chord gets padded or looped to fill its duration based on the tempo. And then step 5 is the output. We upscale the final audio from 16 kilohertz to 44.1 kilohertz, which is standard audio quality. And because of that, we can save it to an MP3 and a wave. And the 16 kilohertz is the limitation of the NSynth model. So the upscale doesn't add any new frequency content. It just makes it playable on like a standard audio software. But it still sounds like 16 kilohertz. So it sounds like a really compressed audio. And for the evaluation, since there isn't like a standard quantitative metric for audio synthesis quality, I'm evaluating through like the spectral analysis. The pre-trained keyboard model does produce recognizable pitch sounds. You can hear, which I will demo after, you can hear different pitches when it's generated individually. And the chord does sound like chords. It does not sound like pure noise. It did in my first couple runs, but then after some iteration, it started to sound like something. Looking at the spectral analysis, the waveform on the left shows a consistent energy throughout the audio with some like amplitude variations here and there. On the right, the MEL spectrogram shows energy concentrated in the lower frequencies, which is what we'd expect for a keyboard or a pad sound, but the energy is very diffused along the rest of the spectrum. Instead of showing like the sharp lines that you would expect for pitches. Yeah, this tells us the model is getting like the general pitch right, but it's not producing the crisp, like the exact sound that you want to hear from a real instrument. And this goes down to the limitations. The 16 kilohertz sample rate caps everything at 8K hertz, which cuts off the brightness that you would normally hear, and it also sounds like super compressed. The model only generates half a second at a time, so longer notes loop. And at only 125,000 parameters, the model doesn't have the capacity to produce clean like harmonics. For comparison, production quality audio models use hundreds of millions of parameters. And one interesting finding was that the pre-trained model trained on thousands of keyboard samples actually outperformed the version I fine-tuned on just 332. Um, and so more data beat like just the domain specific tuning in this case. And then for related works, flow matching is the theoretical foundation of our model, like we mentioned. They talk about how you can do generative modeling by learning simple velocity fields along the straight interpolation paths, which is where that equation came into. And then for NSynth, that's the data set that we're using. It was originally introduced by Google Magenta for a neural audio synthesis research and contains around 300,000 labeled instrument samples. And every sample has a clean MIDI pitch label, which is what we wanted for our pitch conditioned generation. And then Refusion is probably the closest work to what we're doing like conceptually, because they also generate music by generating spectrograms. They use stable diffusion at a much larger scale with text conditioning. Like you can type in jazz piano and it can generate that. Obviously, our approach is smaller and it uses pitch conditioning instead of text. And DDSP takes a completely different approach. Instead of generating spectrograms from scratch, they combine neural networks with digital signal processing building blocks like oscillators or filters. This produces much higher fidelity audio because the DSP basically guarantees like a clean structure. It's a good example of where our approach could improve. But yeah, and let's move on to the demo. Cool. So we can go ahead and drag in the MIDI that our task one produced, which is right here into FL Studio. And this is what it made. So as you can see, it kind of duplicates this like either 3 or 4 chords, and then it transposes it up 12 semitones. And it kind of does that. And I think it was also really interesting because this is a tactic that I use personally when I produce my own music and I write chords. And I don't know a lot of music theory, so I don't know how common this is. But the model has these 3 chords and then a fourth, which is similar to the second. But when it repeats, the first 3 chords are the same as these, but the last chord is different in relation to the 4 bars, which I thought was like super interesting. So let's hear how it sounds with a pad myself. So if I go in and then I load up, some kind of like synth that I've used recently, this is what it sounds like. Which is really cool. And if I drop my tempo to around 121 and then I, basically double time it, it can sound pretty cool. You can continue messing around with it. You can get some really cool patterns and really cool music that I would honestly like use in my own production. Like if I just slap this kind of filter on it. Yeah, so super cool. This is the MIDI that it produced. Obviously, this is after some tweaking, but that's the MIDI. For the actual output of task 4, this is where it starts to get a little funky. Because of the 16 kilohertz limitation that we had, it sounds super muffled and very compressed. And that is this guy right here. And this is the synth that our model spat out. What I think is interesting is that instead of using a 4x4, it used like a weird 3x4 kind of, where it's 4 bar measures, but there are 3 inside of the like each of the bars. But it sounds like this. which you may think sounds really weird, but compared to my earlier renditions, it sounds much better. This is what it did sound like before. Just no sense of any musical presence at all. So definitely huge improvement. But yeah, so that's the demo. Hope you enjoy my presentation.